was it? There was an exercise on Lagrange multipliers, right? It was writing the posterior distribution using base formula for the binary symmetric channel for parity check codes. And proving properties of the Shannon entropy. So we're not in a hurry today because I don't want to do so many things, so we have time to do things smoothly. So maybe each of you can try and show me your reasoning and how you got something or not, and we discuss together. Okay. So who wants to? Maybe we can start with the parity check code. Okay. So who feels if you want to try? Okay. Maybe you can write there. I think the others will see what you write. So maybe you can recall the setting. Yes.
Yeah, I did.
So this is the communication channel,
Yes.
and this is the noisy bits. Okay.
What I actually did was just repeat everything with her.
Yeah. So the thing you had to think about is how can you model that with a probability, so conditional probability. Yes, so conditional on X, each noisy bit is independent of each other. So by independence, you just have the product of their. These are called conditional marginals. Okay.
And with the indicator functions, whereas if I have 1 minus epsilon is and epsilon when 1.5 is the.
Yes, very easy. Okay. So if you want actually this you don't need, and you want to put a big parenthesis here. Let's close with this one. So yes, very easy. Okay, so this is the joint probability of the noisy bits, and therefore you can finish the reasoning, even if it's exactly the same as yesterday. You can, from there, can you write the posterior and explain us how you do? Okay, so this channel, so what I call channel, the channel is the vocabulary from communications, okay? So what we call a channel, mathematically, it's this conditional distribution, okay? So the channel is the distribution of the output of the communication channel given the input. And we always assume models where the noisy outputs are conditionally independent, in the sense that when you fix X, it is a product over the noisy outputs, okay, over the noisy bits. And indeed, this rule is written probabilistically in this way. So with probability 1 minus epsilon, the noisy bit will be correct. It will be the input bit. And with probability epsilon, it will have been changed. Okay? And indeed, if you sum this object over the possible values of yi, which are 0 and 1, you get 1, because you get 1 minus epsilon plus epsilon. Okay, so it's normalized. And this also is normalized. Okay, if you sum this whole product, you get 1. Okay. So now, how do you get the posterior? So this is the, this is called the communication channel in communications. Or the noisy channel. Okay, but mathematically this is just a conditional law or conditional distribution, or in the language of inference, of Bayesian inference, of Bayesian statistics, this is called the likelihood. Okay? Likelihood in the sense of this is the likelihood of observing the data Y, given that the signal, the information, is X. Okay? The unknown information takes value X. Okay. Okay, so then maybe what is the next step? It's to write Bayes' formula. The posterior is the product of the likelihood times the prior divided by the normalization, which is the sum over X of the numerator. And this is also called in Bayesian statistics, it's called the evidence. It's the marginal probability of the data. It's called evidence. Okay? Okay, and so maybe you can write it explicitly.
First the code.
Sorry?
The code.
Yeah, so maybe what we can do is to erase just this.
Okay.
And you can use what you already wrote here. Yes, times.
The prior.
Maybe you can write it there, times this product here.
Okay.
And so the prior in this case is what? Is a measure, is a law that will give uniform probability to all code words, to all binary strings that actually belong to the code. Okay?
Can I write it this way?
Sorry?
Can I write it another way? I forgot the notation that we used.
So
Or
try to write this as a product of parity checks. Because so we said that the code is defined by a set of parity constraints, and the code word is a binary string such that all parity checks are verified. So it means such that if you take the product of the indicator functions associated to each parity check, their product must be 1, which means that there is all parity checks are verified.
this can be
In some A, yes, some set A, that's perfectly a valid notation. But here, this is just a number. An indicator is an event.
Okay.
So you want this to be equal to 0, yes, which means that the sum of the bits is even. Okay?
And then everything is
No, there is no other index because in her notation, she defined all the J's, all the indices that belong to a set, and this set defines the parity check. Okay? So it's a compact notation, which is very appropriate. And this is the evidence. Good. And this, yes, great. Okay? Thank you. So, you see, once you understand a bit this Bayesian framework, it's you now understand how to write this type of probability distributions. But so what I want to emphasize again is that you can write it like this, but then if you want to do inference, which means to use, so inference are 2 steps. The first step is to define the probability distribution that represents the information that models the information you want to recover given some data. Okay, so to write down the posterior, which is what we wrote. Again, the posterior, the probability that the signal takes some value x, given that the data that we observed was y. And this posterior is the proper distribution to model this signal given the data. Okay, this is the first step. But the second step is, of course, to use this probability distribution to actually infer the signal, the information, to recover it. And in the context of communication, it means to correct the errors. Okay? And so an error correcting code is essentially an algorithm that will to get an estimate of what were the bits that were transmitted. And we understood yesterday the mechanism that even if some of the bits are erased due to the communication channel, because we have these parity checks here, okay, these constraints allow you to recover the bits that were erased. You remember the mechanism? Okay. If one of them connected to a parity check has been erased, maybe the two other ones are not, and therefore you can recover it. And once you recover it, this will allow you to recover some other bits that were erased and connected to parity checks that are connected to the ones you just corrected, and so on and so forth. And you have a propagation like this of corrections. Okay. And so, of course, this is what I will not discuss, but what you would like to do, for example, if you have this distribution, your estimate of the code word, your best guess for what series of bits was actually sent, so what code word has been transmitted, would be, for example, take the argmax of this probability measure. Okay? But this operation may be very difficult to solve. This is a complicated optimization problem. And error correcting codes are algorithms that are trying to solve this optimization problem in an efficient way. Okay? All right. And by the way, you can rewrite, you can take the exponential of the log of this numerator, and this defines the Hamiltonian of the problem. Okay? Where you have, I wrote that yesterday, you want me to rewrite it, or we have a sum over I in the Hamiltonian of the logarithms of these terms, which are kind of local external fields, because they depend only on a single spin, on a single bit. Okay? So they are one body interaction, which we call external fields in physics. And you will have plus a sum here. You wrote a product over I. I'm not sure it's correct. Maybe what you want to write is a product over A, which belongs to, I will call P like this, which is the set of parity checks that define the code PC. Okay. This is the set of parity checks that are defining the code. Okay? So you will have a sum over A of the logarithm of this indicator function, and this defines multi-body interactions. Okay, so we get a kind of Ising model. Okay, because the variables are binary with interactions between spins due to these parity checks, and these are these interactions that allow us to correct the errors. Okay. External field, multi-body interactions. Okay. The next thing, maybe we can prove some properties of the entropy. So who wants to write that? wants to try to prove one or two things of the entropy? Maybe you can do the Lagrange multiplier. You sent me the.
What is that?
Yes. You want to try to prove a few things about the entropy? Don't be shy. Huh?
Try.
Yes, you can try. So let's try to prove, for example, which one did I ask? I don't know.
The first is that
The chain rule? Yes, let's prove the chain rule. So h of x given y plus h of y equals h of xy. Let's try to prove that. So I would start, actually, I think it's easier to start from the right-hand side, from the definition of the joint, of the entropy of the joint.
So
Yes.
this is the entropy, the inference entropy. So it will be this one, x1, and 1 over x1.
Yes, of course.
And this one is c of x x given y
Yes.
times the probability of this y.
Yes, so you use the product rule, or it's equivalently just the definition of the conditional probability. Yes.
And over, and this one
The same, yes.
of x given y.
Yes.
So we need to get this.
You're the first person I see having so much fun proving the chain rule. It's great.
Get it?
It's correct. Continue.
Okay, so I think first we get use the property of ln.
Yes. Maybe instead of what? Yeah. Continue.
And sorry. Is it if I do a negative? Is it is it correct? Okay.
So yeah, okay. Yeah. Maybe you can do two operations at the same time. What is log of 1 over x? What is log of 1 over x in general? How can you write? Maybe you can do two things. Okay.
Wait, so I can bring out the.
Yeah, exactly. Directly, simpler.
X1. Then
It's okay. Yeah, but now you're in master. You can do. You don't need to write every single operation for every line. You could rewrite this so you can separate the sum if you want, but why not? But directly, what do you get with that this term before. What is that?
That's what I'm not sure because if this one from the definition will be.
So you don't need to rewrite it. This is exactly the definition of this.
With this.
Yes. Yes. So this term is exactly h of x given y. Okay, and this term is what?
So this is h of y.
Yes, but why? Because in reality, h of y is just this with the sum over y only. Right?
Yeah.
So why is it the same thing? So this, does it depend on x? Should not overthink. Huh? Does it depend on x? Do you see x here?
So the summation for this side will be 1 y on y.
Yes.
So the dependence on x is.
Yes, exactly. This is independent of x, this as well. So you can just sum this thing over x. And this is a probability distribution. So it's 1. What?
You are saying that she cannot hear it.
Okay. Done. Okay. Good. What was another property? I mean, the other properties are exactly the same type of proof. Huh? It's just distributing a log, or so maybe it's okay. Okay. If there is one property you don't manage to prove, come to see me. But it should be. There is nothing more complicated than this. Huh? Just have to exploit that probabilities are normalized, that the log can be distributed, that log of AB is log of A plus B. It's the same level of difficulty. Okay, so maybe we can move on. And so can we do the exercise on Lagrange multipliers?
Yes.
Okay, so maybe you can explain this. Try to speak loud so that Anna and everyone can hear.
Okay, so we have a function.
So maybe you can start a bit more on the top, otherwise you will miss space quickly. If you manage.
Okay, so we're given a function. Where do I go?
No, if you stay on all these blackboard, they see. You can.
So our given function is 2x plus 5, and our constraint is which is also g of x squared. Well, it's given by the circle x squared plus y squared is equal to 1, and we can rewrite this as 1 minus x squared minus y squared is equal to 0. We're going to define the Lagrange
So,
function.
yes, okay. So, can you write the constrained optimization problem that you're trying to solve? This is the constraint. Can you write really the constrained optimization problem?
I only have notes. So.
You only have what?
The notes. This one?
Yeah, can you write the problem that you're trying to solve? Just essentially.
The Lagrange?
Yeah, no, but the definition of the problem. You will use the Lagrange multiplier method to solve which problem? You don't need to look at the notes. Just think. What is the problem you're trying to solve?
We're trying to find the maxima and minima.
So, yeah, write that. You're trying to find.
Just write it in words.
I mean, write it in.
The maximum.
So yeah, maxima or
So we're trying to
write
find the optimum.
Optimize.
We're trying to optimize. I can't really. Optimize this function given this constraint, and optimize just means that we have to find the maxima and minima.
No, just write optimize f of x, f of xy, optimize f of xy.
Given
Such that, yeah, given such that is the same. F of xy. No. C is
the
defined in
constant,
this case.
right?
So, what is the definition of gxy? Because you have not been very clear in defining gxy. Gxy is defined by an equality. What is the definition of gxy?
The function.
What is the function gxy?
This is the function gxy.
Okay, so in mathematics we don't write dot dot like this. We write equal. Y is equal to x squared plus y squared. Okay. So what is the constancy?
Constancy in this case is 1.
Okay, so write 1. Okay.
Okay. And then we're going to define the Lagrange function, which is basically f of x minus plus our Lagrange multiplier lambda into x minus into 1. And we run out of space.
What did you write?
I'm sorry?
You wrote?
So
No,
we're just going to
this
define.
means nothing. Look at what you wrote. You
Yeah.
wrote, this mathematically means nothing. No. Let's understand. What you wrote means nothing here.
But we have to define this function. Right?
No, this is not a function, what you wrote. This is an equality, it's not a function. So this cannot be a function if this is not a function.
Okay.
You are summing a function with something which is not a function. This is an equality.
Okay.
So this is not what I defined yesterday. What I defined yesterday is the function minus the constant.
Yes.
It's not the same thing. Now this is a function.
I understand. And then we take the partial derivatives with respect to x, with respect to y, and with respect to lambda. So this is just 2 plus 2y. And because we're trying to find the maxima and minima, we need to equate it to 0.
You got the answer also? Did you try? tried and you didn't manage, or you didn't try?
Sorry, Professor.
Yes.
So
Can you hear me?
Yes.
The volume is low. We can't hear very well.
Yes.
I think that is a technical problem. They say that they are looking for.
oh, because I'm not whispering anymore.
So I cannot do much, and I'm sorry that we try. Yeah. So continue.
Okay. Yeah, so we have these partial derivatives now, and now we're going to just find the values of lambda.
So, by the way, when you write a Lagrangian, first what you wrote is not correct here.
Okay.
Because the partial derivative of this thing is this minus 1.
Yeah.
But once you wrote a Lagrangian, computing the derivative with respect to the Lagrange multiplier is not useful, because by definition, this will just enforce the constraint.
Okay.
Okay, so what I'm saying is that this, you will use this equation at the end to fix the value of lambda, but you don't need to rewrite this, because you will just always get, again, the constraint that you wrote.
Yeah.
Okay. So you have two equations.
We have two equations to find.
You actually have three equations for three unknowns.
That's why I wrote this.
Yes, but what I mean is that in practice, you don't need to rewrite each time this thing, because what you get is always the equation which defines the constraint.
Okay.
You will not get something new. Yes.
Lambda should be if lambda should always be the sign or the dimension of the f of s, then.
Sorry?
Lambda is a vector.
No, here lambda is a scalar here, because you have just one constraint. So we have just one Lagrange multiplier. You have one Lagrange multiplier per constraint, and here we just have one constraint.
So how about the x and y?
X and y are two scalars.
Okay.
They're two. Yeah. F and G are functions from R2 to R. Okay.
Yeah. So there. Lambda from here, and here we get lambda, and we can plug this back into this to get values for x and y.
Yes.
And when we do that, we first will get values for lambda, and then we just plug.
Yeah, so you have re-expressed, you have solved for x and y as a function of the Lagrange multiplier. Now you need to use the last equation you have, which is the constraint, to close the system and to find the value of lambda. Yes. Do you hear better, Anna? Anna, do you hear us?
Yes.
Is it better now, the sound quality?
Yeah, it's better. Thank you.
Okay. That's it. Yes. So you have a quadratic equation for lambda. Okay. So it has two solutions. And these are the two solutions, okay?
Yeah.
And the last thing you need to check is,
You need to put it back in here to get values of x and y.
and you get two solutions. Yeah.
Yeah, sure, I'll do that.
So you know that these two solutions are two optima. And then what you need to check is which one is the maximum and the minimum. Maybe in more complicated problem, you may have more than two solutions. Huh? But let's say you have k solutions. Then if you're looking for the maximum, then you need to plug this k solution in the function f, and just to check which is the maximum. Okay? And here you don't even need to check. This is linear in x and y, so the max is given by the solutions where x and y are higher. Okay. Okay, that's correct.
Yeah. So I run out of space, but
So you have a plus solution in this case and a minus solution. And of course, in this case, the maximum is given by the plus solution and the minimum by the minus solution. Okay? Yes.
and
Yes. Just the symmetric of this.
Yeah.
Yes. Thank you very much. Okay. So now what I want to do is to use this method to derive from the entropy the Boltzmann distribution, or actually generic forms of distribution. So maybe now I can continue there. So maximum entropy principle. So the maximum entropy principle is essentially telling you that if you know something about some random variable, that can be a huge vector of microscopic configurations that can describe a very complex system. And let's say, yes, you know some things that are verified by this system, okay, and you would like to find a probability to describe this system that includes this knowledge that you have about the system, okay? And this knowledge can be formalized mathematically by a set of constraints of this form. You know that some function of the random variable that interests you must be constant. Okay? And you know some constraints of this form, but you know nothing else. Okay? You don't know anything more than this constraint. Then the maximum entropy principle tells you that what you should do is to find a distribution that maximizes the Shannon entropy under these constraints. Okay? And what does it mean? Maximizing the entropy means maximizing the uncertainty we have about this random variable, but taking into account what we are sure about, which means these constraints. But if you maximize your uncertainty under these constraints, it means that the distribution that you will get from this principle assumes nothing more than this constraint. It is maximally uninformative about the system under these constraints. Okay? Is it clear? It means that this distribution encodes no more information than this constraint. No less, no more. It's the maximally uninformative probability distribution, in the sense that it has maximum entropy, but under some constraints that you know are true and that you fix. Okay? So I will do now, instead of writing what I just said in sentence, let's directly look at examples. Okay. So what is the minimal assumption about a probability distribution? Let's say you know nothing about some random variable, except that it's a random variable. What is the minimal constraint verified by the probability distribution? Yes, that it is normalized. Okay, if you know nothing about a random variable, the only thing that you know actually is that its probability distribution, by definition, must be normalized. Okay. So let's say that you have an ensemble, which is a vector x, a random variable x, that belongs in, that have configurations xn, and some probability p. So we want to show that using the method of Lagrange multipliers, that the max end, which is the shortened version of maximum entropy principle, leads the uniform distribution when nothing is known about p, except that it's a probability distribution and therefore that it is normalized. So the max end, in this case, under no assumption about x, is what? You should maximize the Shannon entropy. And here I will use this alternative solution notation that I also introduced. You know that we can write the entropy of a random variable, which is the same as writing the entropy of its distribution. Okay? Because the entropy is a function of the distribution. It's sum over x of px log px with a minus. Okay? So I think of this entropy as a function of the probability distribution. And because we are considering discrete random variables, this probability distribution, I can think of it as a vector of numbers, which are the probabilities of each outcome. Okay? This probability distribution P, I can think of it as a vector P of x, indexed by x, where x are all the possible outcomes. You agree with me?
Yeah.
For example, for a coin, you have head and tail. The probability distribution is just parameterized by two numbers, actually one in this case, because if you know one by normalization, you know the other. But it's just a vector of two numbers, which is the probability of head and the probability of tail. Okay. So we think of this probability distribution as a vector indexed by the possible outcomes. Okay? So I want to maximize this entropy, which is a function of this vector with respect to P, such that sum over x of px equal 1. Okay? If you know nothing about a random variable, you know at least that its distribution must be normalized. So this is the minimal assumption. Okay? So here we have a constraint optimization problem. So the method of Lagrange multipliers should give us the answer. Okay? So let's solve it. I define a Lagrange function, which will depend on my vector of probabilities. And on a single Lagrange multiplier, we have a single constraint in this case, which is what? Which is my entropy. So let's write it explicitly. Minus lambda sum of x of px minus 1. This is my constraint. Okay. Now, if I look at the partial derivative with respect to what? I should take a derivative with respect to?
No, not lambda, because we just get that.
Lambda, we don't need to take partial derivatives because we will equating it to 0, we just recover this.
So, all the
What?
P of x?
P of x or x?
P of x.
P of x.
P of x.
Here.
Yeah.
The parameters are these probabilities. P of x.
But all the probabilities from 1 to n.
So here I fix one. I fix a given x. Let me call it, if you want, x star. It is one given outcome, and it is its associated probability. Okay. Equals 0. And what do I obtain? I obtain minus log px star minus 1. This is the derivative of this term. Minus lambda, and that's it. Okay? And so what do we obtain? We obtain that P of x star is proportional to a constant. Because I can put all that on the left-hand side, take the exponential, this just gives me a constant. We don't care what this constant is. But now we use our second equation, I mean our last equation, because here we obtain this for each x star, okay? For any x star that belongs to the set of possible outcomes. And now we use our last equation, which is the constraint. And so we know that P of x star by normalization must be equal to 1 over this cardinal. Okay? So the method of Lagrange multiplier, sorry, the max entropy principle, assuming nothing about the system except that you want to describe it with a probability distribution and therefore this function P must be normalized, gives you the microcanonical distribution, which is a uniform distribution. Okay? So if you know absolutely nothing about a system, in order to design a distribution that represents your absolute lack of knowledge, the distribution which has maximum uncertainty is the uniform distribution. Okay? We recover what we said. Now, let's do that for another distribution. Let's do that for, let's directly do Gibbs. So what is the only thing we know when we place ourselves in the canonical ensemble instead? So in the microcanonical ensemble, we know nothing. It's like we have a system of particles totally isolated. There is no transfer of energy or anything with the outside world. It's like a black box. So we know nothing about what is going on inside. Therefore, the distribution is uniform. We just recovered from the maximum entropy principle the fundamental postulate of statistical mechanics, but from an information theoretic point of view. From the fundamental definition of entropy, of information, which is the Shannon entropy, and using the maximum entropy principle, we recovered the fundamental postulate of statistical mechanics. Okay? So now, in the canonical ensemble in statistical mechanics, which is the unique constraint that we have, what is the only thing we know about the system? Speak louder. Each time you look at me, you say like, and then you smile. It's really nice. Don't be shy. Go for it. I'm sure you have the good answer. Actually. You don't need your notes. You know it. Tell me.
What is temperature?
So temperature is just a word. Say a statement. What do you mean?
Constant.
Sorry?
The temperature is constant.
The temperature is constant. No, the temperature, actually you can see it in one way or the other, but usually if the temperature is, so in the canonical symbol, we assume that we have
Macro
this box.
state?
Sorry?
Nothing, continue.
No, say it, say it.
Macro state?
Again, this is
La
just
de-
a word. Actually,
macro
in this
state.
scientist, when we say something, we say a clear statement. So what is your statement?
The only information that you know is the macro state, like the temperature, energy, or
The
that.
temperature in the
Something that you
canonical-
can.
Yes, the temperature in the microcanonical state is not considered as an order parameter. It's not defining the system. What it's a control parameter. It's something that, as an experimentalist, you can fix. So it's fixed by the heat bath, so the external world. Okay. But so if the temperature is fixed to something, what it implies is that the of the system is fixed. The what? The energy, the internal energy, which means the average energy of the system. Okay. So of course, these two parameters, the internal energy and the temperature are dual of each other's, in the sense that you can think of fixing the temperature, which implies that the internal energy is fixed to some value. But of course, you can also think that in some way you could fix the internal energy to some value, and there exists an associated outside temperature which corresponds to that. But as physicists, the way we think is the other way around. What we fix is actually the temperature of the outside world, which implies fixing the internal energy. Okay? But of course, it's dual. Okay. But indeed, what we know is by controlling the temperature, the only thing we know about the system is that its internal energy is fixed. So its average energy is fixed. Okay? It's not anymore constant. It's allowed to fluctuate thanks to thermal exchanges through the walls. Okay? But the average is fixed at equilibrium. Okay? We are always talking about equilibrium systems. There are no global fluxes of heat between the inside and the outside, so that the average energy is fixed. Okay. So indeed, in the canonical ensemble, the only thing you know is that the internal energy, which means the expectation with respect to the Boltzmann measure of the Hamiltonian, is equal to some value. Okay? Okay. So let's apply our max entropy principle. So we maximize. Yeah, by the way, instead of writing optimize, you see in the previous slide, I also wrote maximize. I can allow myself to directly maximize because this is an exercise. You can check that this function, actually we already did this exercise. If you think it as a function of the vector of weights p, it is a concave function of these p's. And here you have a concave function. The Lagrange function here is a concave function plus a function which is linear in p. And the function which is linear is both concave and convex. It's the limit between the two behaviors. So if you add a linear function to a concave function, it remains concave. Or if you add a linear function to a convex function, it remains convex also. So this Lagrange function here is concave in these parameters px. in each parameter px. Okay? So the only possible optimum of a concave function, first it is unique, it has a single one, and it has to be a maximum. Okay? So instead of writing optimum, I can directly write maximum. Is it clear?
Yes.
But in general, you should check for more complicated functions. If you don't have concavity or convexity properties, you should be careful if what you compute is a max, a min, okay, or even a saddle point. Sometimes it can be not nor a max nor a min. Maybe it's a max in some direction of the space, or it's a min in some other direction. Okay. But here we know it's a max. So, and again, I think of this probability distribution as a vector of weights, such that first constraint it is normalized, and second constraint the average of the Hamiltonian is some constant E. Okay? So I define the Lagrange function. And now I have, now the lambda now is a vector. Okay, I have two Lagrange multipliers. So it is what? It is the entropy. We have a first Lagrange multiplier for our normalization constraint. And we have a second Lagrange multiplier for our average energy constraint. Okay. Just a remark so that you're not lost if one day you see people writing Lagrange functions slightly differently. You see that actually, if I would not write this or this, it would not change anything. Because when I take derivatives with respect to p, okay, here. You see that these are just constants. We do not care at the end. It's nice to write them to remember what's the meaning of this function, but to compute, when you want to compute things, you do not care about writing this constant actually. These constants at the end, you can just remember when you took derivative, what are the constraints you want to verify. You see? So, okay, that's just a side remark. Okay. So now I take a partial derivative with one given parameter, which is a probability of x star, for example. And I obtain, as before, minus log px minus 1 minus lambda 1, that's it, minus lambda 2 h of x star. Do you agree? Equal to 0. It's okay. So I isolate my log px, my px, and what do I obtain? It's proportional to a constant times exponential of minus lambda 2 h of x star. Okay. Now, by fixing properly the value of my lambda 1, I verify the first constraint. So the first constraint tells me that this thing is normalized. So I know what is this constant. It is 1 over sum over x of exponential minus hx, okay, times lambda 2. So this, by fixing the value lambda 1, I normalize my distribution. And therefore, this second Lagrange multiplier, I would need to find its value in order to fix this constraint. But this E here that I wrote is generic. We don't care. It's not a specific value. It's generic. There is some value of lambda 2 such that if I find it, there is a lambda 2 of E that exists and that fixes the average energy to E. And therefore, this lambda 2 is what? It is my beta. It is my inverse temperature. So there is a temperature, or equivalently an inverse temperature, that depends on E. Okay. So that my average energy is equal to E. So you see, we got two things extremely nice here. First, we derived the Boltzmann distribution. This is exponential minus beta h x star over z. And also, now we understand why, without calling thermodynamics, why fixing the inverse temperature is controlling the internal energy. Because this inverse temperature here is a Lagrange multiplier. Okay? So by fixing the value of the Lagrange multiplier, you can verify the constraint of fixed energy. There is a value of this Lagrange multiplier that fixes the internal energy to whatever value you want. Okay? So this inverse temperature here has a very, this Lagrange multiplier has a very clear meaning. Okay? So now we understand that the Boltzmann distribution is the maximally uninformative law for a given system under the constraint that its average energy is fixed. If you know nothing else than this about some system, then the Boltzmann distribution is the proper distribution to model it from the information theoretic point of view, in the sense that distribution assumes nothing else than this constraint. No less, no more. Is it clear? It's beautiful, no? It's nice, huh? And for me, I find it extremely powerful. Okay, let's do one or two examples more. Maybe you can try at the blackboard. You didn't try an exercise. Come, let's try. So let's use the maximum entropy principle. So what we want to solve now, let's say that you have some system. Okay, you have a complex system described again by an n-dimensional random vector, which is representing the microstates, okay, the configuration. And for some reason, you know what we would call in physics the local magnetizations. So you know what is the average of each of these variables. Okay? And that's the only thing you know. Okay? So it's like, for example, you can think about a spin system, and these spins are fluctuating so fast that you don't have an apparatus able to probe the dynamics, but you can measure what is the position of the spin, but average over a long time window, over a time scale which is much larger than the time scale of the fluctuations of the spins. So it's like if it's integrating over a large time window. So what you measure is the average position. Okay, if in average it's more up or down, and it's called the magnetization. Okay, the local magnetization of each spin. And you know that for each spin. Okay, so the constraint is that the local magnetization, which is sum of px xi, so you look at the ith component, is equal to mi, to some value that you can measure. Okay, for all I equal 1 to n. Okay, for each spin. And of course, we always have the normalization. But you know what? I mean, now we know that we're always looking for a distribution. So in some sense, we can drop this constraint and always normalize the function that we obtain. Okay. It's always implicit that we're looking, in a sense, I can forget this constraint and write instead MP probability. P proba. So now whatever function I will obtain, I will then normalize it at the end. It's the same as considering a generic function and adding this constraint. Okay? It's just the 2 point of view. So let's forget this constraint, and implicitly we'll anyway at the end normalize what we obtain. Okay? All right, can you try to solve this problem? Come. So the Lagrange function, so what you wrote is already not correct. Try to be precise. Yes, and it also depends on something else. No. Yes, you have a vector of Lagrange multipliers. Here, how many Lagrange multipliers will we have? N. We have n constraints. We have one constraint per spin. Sorry?
In order to solve it, like instead of solving n equations, should we just fix it to 1?
Should fix what to 1?
I.
I don't understand.
So if we have n multipliers, we need a lot n plus 1 equations to solve the problem.
Yes.
So are we going to do that?
No, the point is that we think of this magnetization mi as parameters, and it's like in the Gibbs, distribution, the Boltzmann distribution example. If you fix the internal energy to some value,
Yeah.
There exists a Lagrange multiplier that fixes it to it, that corresponds to. But we didn't solve explicitly for this Lagrange multiplier. This may be a very complicated problem.
Yeah.
What we want just to obtain is the generic form of the distribution as a function of these Lagrange multipliers,
Okay.
without really solving for the Lagrange multipliers for specific values of mi. We just know that there exists some specific values that fixes the magnetizations to this mi, but we don't solve it explicitly. Okay? And actually solving this kind of problem may be very hard, and I will say a word about that. It's a good point. Yes, that's the correct object. So if you use a specific X star, it should correspond to the same X star here. You can now think, well, yes, here it's a, but let's try it, it's not that I want to be picky, it's just that you need to learn to be precise. So this function depends on lambda as well. You wrote lambda. Okay. This is the whole vector of probabilities, where you can see the outcomes as an index. And here you're taking the derivative with respect to one of components of this vector, and this component is the X star component. Okay, continue. Are you sure? Are you sure? Are you sure? Think. Yes. No.
Seems this I don't know.
Okay, independently of whatever you're going to say, this cannot be right, because you see that this is a linear function of these probabilities. And you're taking a derivative with respect to one of them. If you take a derivative with respect to a linear function, you should get a constant with respect to this parameter. So this cannot depend on P. Is it clear what I said?
Yeah.
So you see it, the clean way to think is that these sums, you have two linear relations. You can switch you have two linear operations, which are sums. You can switch them. This is the same thing as sum over x of P of x of xi. What do I want to write? Yes. Sorry, I have sum over I, lambda I xi, plus things that do not depend on P of x. So I don't care. So the derivative of that with respect to one of the terms, one of these terms here, gives what you wrote. Okay? That's correct. And sorry, no, there is still sorry, there is a mistake. Yes, so when you take this derivative, you picked this x star is a vector. Huh? So you picked one vector x star. And so in this sum, you picked one term here and it should match with this one. So here you have a star.
Yeah.
You agree?
That if you match this thing, that means we do not have this summation.
No. This summation is over I. It's not over the index x. Here you have two indices. You have x, which is the outcome.
Yeah.
And x is a vector of size n. And you have index over I, which is the spin index. It's the components of this vector.
Yeah.
So by picking one term here in the x, you're picking the x star term, which is why you put a star, but you still have this sum over I. Is it okay?
Okay.
So what do you obtain? So all that must be equal to 0. You must optimize this Lagrange function. So write it equal to 0. You're looking for the optimum of this Lagrange function. Again, here this function seen as a function of the px is concave. So we know that anyway there is a single optimizer, which is a maximum. So here it's not really equal because we forgot, we still have in mind that we have the normalization constraint. P must be a probability. So here you have a proportional sign. And you can put an equality once you normalize. Okay? Yes. Yes, and this constant is the normalization, is sum over all x's of the numerator. Okay? Thanks. So P of x is 1 over z exponential sum of I lambda I xi. So what is that? You see that we have a distribution of independent spins. Okay? We have an exponential of a sum, which is the product of these exponentials. So the measure that we constructed is factorized over the variables. Okay? So under this single constraint here, the best thing you can assume is that the variables are independent. You cannot deduce more from this constraint. And what are these lambda i's? These are local fields. These lambda i's are local external fields. Okay? So you see there is again a duality between local external fields and this time local magnetizations. By fixing the values of these local external fields that are actually Lagrange multipliers, you are fixing the local magnetizations. Or vice versa, for some given values of of the local magnetization, there exist values of external local fields that correspond. Okay? I do a last example. Now assume that in addition of knowing local magnetizations, you know more. You also know local or two-body correlations. So you know that xi, xj, if you average xi, xj, you get some constant Cij for all ij for 1 to n. Okay? Or with our statistical mechanics notation, this is this. Okay? These are called two-body correlations. Actually, often in physics, what you call correlation is this removing the product of the local averages. Okay? But here, I will simply consider that. Okay. You see, it's an information that connects two spins. So it's a correlation. Okay? So the Lagrange function, can you guess from what we did here, what will be the Hamiltonian will zero? Here the Hamiltonian is just the sum of one-body terms. Okay, so it's a very simple Hamiltonian. It's a decoupled Hamiltonian. There are no interactions. Okay, they're just one-body terms. In terms of factor graph, it's like if each node is connected to a factor, and that's it, an independent factor. What will I obtain now with these new constraints?
We have an extra term, summation over the coupled term.
So T you will have what, sorry?
You will have another summation of, like, there will be another term in the exponential for the coupled term.
So summation over?
Summation over ij.
Yes.
And yeah, ij, there will be another lambda.
You will be one lambda ij, so one Lagrange multiplier per constraint like this.
Yes.
Now we have n constraints here, and we have n squared over 2, essentially, constraints here. Okay? And so I don't do the exercise. Now you got it, you can do it. What you will obtain is P of x is equal to 1 over z, exponential of what? Exponential of sum over I lambda ixi plus sum over ij lambda ij xi xj. And this is what? This is minus the Hamiltonian of the Ising model.
Wow. That's really cool.
Where the lambda ij's are what we call in physics jij, and the lambda I here are the hi, the local fields. You obtain a disordered Ising model. Okay. So what we just proved using information theory is that the Ising model is the minimal model to represent correlations, two-body correlations between variables. Okay? If you would have information about 3 points correlations like this, you would obtain a generalized Ising model where you would have in the Hamiltonian a sum of 3 spins like this over 3 spins, and so on and so forth. So the more statistics you know about your variables, in the sense the more higher order correlations, you know, like this between variables. By higher order, we mean averages over products of more and more spins. The more complicated becomes the associated Hamiltonian. If you know the free order statistics like this, if you know the values of such free order statistics, you will get free body interactions in the Hamiltonian. Okay? An Ising model does not encode, is not enough to encode free body a statistics of third order like this. Okay? An Hamiltonian, an Ising model only encodes is enough to represent knowledge about local magnetizations and two-body interactions. And it is the model you should use in order to present such complex systems if you have this type of information. Okay? So by the way, and this answered the question you asked previously, if now you were really fixing these local magnetizations and these two-body correlations, let's say these are actual numbers that you measured. Now, finding the local fields and the interactions here, which means the Lagrange multipliers, such that these constraints are really verified for the specific values of Mi andCij's, is an extremely complicated problem. Okay? And it has a name, and there is a whole line of research in statistical mechanics about that. It is called the inverse Ising problem. Just for your okay, why inverse Ising problem? Because the direct, if you want the forward Ising problem, or just the usual problem that you want to solve in statistical mechanics, is the other direction, is you know some Hamiltonian that depends on some specific interactions, X, J, and some external fields. And from there, you want to deduce properties of the system, like local magnetizations, correlations, and things like this. Okay? So the Hamiltonian is fixed, and is, by fixed, I mean that you know what are the interactions and the local fields, and you want to deduce the magnetizations and correlations. Okay? Which is itself a very complicated problem because it requires computing the normalization here, which is a very complicated combinatorial problem. Okay, that's the whole difficulty in statistical mechanics usually, is that once you have the Hamiltonian, in order to compute things like magnetizations and things like this, you need to compute averages with respect to this distribution. But in order to be able to compute averages, you need to normalize this distribution, and computing the sum here is computing a sum over exponentially many configurations, exponential in n, and this usually is impossible. Okay? So the direct problem is a very complicated problem, computing things like this, for example, which are the local magnetization. But now let's say that you know instead this type of things. You know the local magnetization, you have this knowledge or the correlations. Finding the Hamiltonian corresponding to that, in the sense that finding the Hamiltonian such that when you compute these averages, it gives these numbers that you know, or if you compute these 2-point correlations with respect to this Boltzmann distribution, you get these numbers that you know, is also very hard. And it's the inverse problem. You don't know the model. The direct problem is you know the model, which means the Hamiltonian, you want to compute expectations with respect to this distribution. magnetization and correlation. The inverse problem is you know magnetization and correlations. You know expectations if you want. And you want to recover what model gives you these expectations. And both problems are very hard problems. Okay? And equally interesting. Okay. Okay. So I want to say two last things. Now, even more generically, so what we've seen now is that we can essentially obtain the Gibbs-Boltzmann distribution of the canonical ensemble, so the Boltzmann distribution. One point of view was through factor graphs, to define an extremely generic class of probabilities. And we've seen that just by writing them in exponential form, we naturally get the Boltzmann distribution. Okay, that was one approach. And what we've seen now is through information theory and the fundamental definition of information, or equivalently of uncertainty, and through the maximum entropy principle, you get again the Boltzmann distribution. Okay, when you just assume that the internal energy is fixed. Okay, but the Boltzmann distribution is just one way of writing a generic factor graph distribution. Okay, so what is the max entropy principle in order to derive a generic factor graph distribution? It's very easy from what we understood now. If you consider maximizing the entropy under the constraints that the expectation with respect to this distribution of some function, let me call it as GA with respect to this distribution is equal to some number for A equal 1 to some number n. Then, now we don't need to do again the computation. You directly get, you should understand that you get this thing . And this is nothing else than product over A of some FA, where the FA is this thing.
Wow.
Okay? Yeah. Sorry, FA is exponential lambda A JA. Okay, so if you apply the maximum entropy principle under generic constraints of this form, which means that you fix some statistics. What I call a statistics is an object like this. It means an average of a function of the random variable. So if you fix statistics like this, for each statistics that you fix, you get one term, one constraint in the factor graph distribution like this. Or equivalently, one energy contribution in the Hamiltonian with a dependence that comes from here. Okay? So all that is connected.
Everything is interconnected.
Yes. Yes. So okay, here I wrote a small paragraph that I like. Let's continue to relate the statistical mechanics with information theory. So let's continue to interpret from an information theoretic point of view what we just obtained. And what we obtained again is that the Boltzmann distribution is the maximum entropy distribution under the single constraint of fixed average energy. So in statistical mechanics, the first thing you said when I asked you the question, what is the entropy? You said it's a measure of disorder. Okay. So now we understood that it is a very good intuition because information theory shows us that it's the measure of uncertainty or unpredictability of a system, of a random variable. Okay. And this random variable is the micro state. Okay. Okay, so let's consider a simple example. Another example, we gave many. So imagine that you have another example that connects this notion of more disorder is higher entropy. Okay. So consider n boxes, and you have n balls. Actually, this is just, you can also think about n sites and n particles. Okay, this is just for formulating something that we already did, but in other language. Now, imagine that you know, in some sense, that these n balls are in a kind of ordered state. And by ordered here, we mean that wherever are these n balls, they must be all in the same box. Okay, so maybe they're here, or maybe they're here. But wherever they are together. Okay. So this is why what we call ordered configuration. Okay, this is an ordered state. So how many configurations you have? N. Okay, and so the entropy, in this case, H of ordered states, if you want, is log n. Okay, each state has uniform probability, so the entropy is log n. Now, consider instead, okay, so in bits, it's log 2n. Okay. And we said that we can interpret the entropy here, which is really the micro-canonical entropy of the system, also as the number of binary questions you need to answer in order to identify the microstate. So here the microstate would be the location of these balls, okay, in which box they are. So can you find a strategy? What questions, what binary questions would you ask me if you want to converge towards the proper microstate? Let's say that the balls are in one of the boxes. You have no idea which one. Which questions, binary questions, would you ask in order to find the microstate with as few questions as possible? And actually, the number of questions you need will be exactly this. We understood that the entropy was the number of binary questions you need to answer in order to identify the microstate, remember?
Yeah.
It was the information content of the random variable. Here the random variable or the microstate is the locations of the balls. It has entropy log 2n bits. And we said that we can also think of that as the number of binary questions you need to ask in order to identify the microstate, the outcome of this random variable. So which questions would you ask here? And I can only answer yes or no. And if you ask me questions so that you need more than log 2n questions, it means that it's suboptimal. You didn't find the proper question.
Are they on the right? Are they on the left?
Exactly. So the first thing you would ask is, let's say they're here, you would say, are they on the left? And I say yes. So you just discarded half of the configurations. Then you ask the question again, are they on the left or right of this part, of the remaining part? I say yes, no. And actually you will converge exponentially fast to the answer. And you will need exactly this number of questions to find the answer.
That number can be variable.
Yes, but you see that you take a log, so even the log in base 2 of 2 to the power 100, which is infinitely more than the number of particles in the universe, is still only 100. So you see that it's a very, very small number. The logarithm is increasing extremely slowly. So actually, this algorithm, which is called a dichotomy, which each time discards half of the possible answers, converges exponentially fast to the answer. Okay. All right. So you see that the entropy of these ordered states is quite low. Okay, you don't need so many questions in order to identify the microstate. Now let's consider the same model, but now we consider disordered states. The microstates can be disordered in the sense that each ball can be in every box independently of the others. Okay, so now what is the entropy in this case? Disordered case. So the number of configurations is, we already did the same exercise essentially. Yes, it's n to the power n. So the entropy is n log n. So you see that and I will write this in base 2 to keep our interpretation in terms of binary question. See that now we pay a price of having an entropy that scales with the number of particles. Okay, so this is a much bigger number. And what's the reason? What are the questions now, the binary questions you can ask to identify the microstate?
How many parts? How many balls are on what side? But you can't divide it like that.
No, no, because how many particles are on one side is not a binary question.
Oh yes.
I can only answer yes or no.
Yeah.
This is a question which would need much more information.
Yeah.
You are restricted to answers of the type yes or no.
What is the most particle?
No.
No.
That's yes or no.
I can only answer yes or no. Otherwise, you could just ask me what is the configuration and which are the particles. Look, we went from something which is log n to n log n. Because
So for every particle you have to ask.
exactly, you need to do a dichotomy per particle. There is no better strategy because the particles are independent of each other. So for particle 1, you do a dichotomy, you will need this amount of questions. You will need to do the same amount of questions for the second particle. And therefore, you get this number. Okay? And this comes from the independence of the particles now. Okay? So you see this very nice interpretation. If you write the channel entropy in log2 base in terms of bits, you can always interpret this number as the number of questions you would need to do in such a dichotomy to identify the exact microstate in which is your system. Or equivalently, if you observe the microstate of your system, it's like if you got the answer of that many binary questions. So the system contains that much of information. Okay? Okay, I will stop there, I think. Or okay, let me do a last thing. So we've already seen today that the inverse temperature was a Lagrange multiplier coming from the maximum entropy principle under the single constraint that the internal energy was fixed. Okay, so the inverse temperature is the parameter that fixes this constraint. Okay, that's the first one. But let's try to make a further connection with thermodynamics. So what do you learn in thermodynamics? So I think you did that with Roman. What is the thermodynamic definition of temperature? Derivative of what, sorry?
Derivative of entropy.
Of
Entropy. S.
Of S?
With respect to energy.
Yes, that's correct. It's 1 over T. So this is the definition. We write it in this direction. In thermodynamics, the definition of the temperature, which we also call beta, the inverse temperature, which is beta, is indeed the derivative of the microcanonical entropy. S of E is the microcanonical entropy. That is entropy, which means the number of microstates of a system which has constant energy equal to E. So if you change a bit the energy of your isolated system, let's say you slightly increase the energy of this system which is closed, you will put a bit of energy in it and you close it again, and you look at by how much has changed the entropy. It must have increased, okay, because if you put a bit more energy, you allow for more configuration. Then this derivative is inverse temperature. Okay. Okay, so this is what thermodynamics tells us. But can we make the contact again with information theory from that, with what we did today? And the answer is yes. Okay, so how do we do that? The idea is to start from the identification, is to start from the Shannon entropy of the Boltzmann distribution, which is what? Which is okay. You just apply the definition of Shannon entropy specifically to the Boltzmann distribution. Okay. And what's that? So this log gives me minus beta h of x minus log z. Okay. And so therefore, this is what operation, when I apply this operation to something, it is an average, it is an expectation. So this is the expectation of minus beta h x, and this minus, and I have this minus here that simplifies, so it's plus the expectation of log z, but this does not depend on x. It has been already summed over x. This is not a random variable. So this expectation is not there. If you take the expectation of a constant, it gives you the constant. Okay? All right, and the Shannon entropy of the Gibbs-Boltzmann distribution is the canonical entropy, what we call S beta. Okay. And this is the internal energy that we sometimes denote E. And it's a function of beta. Here it's beta times E beta. Okay, I can put this beta outside here. Okay. And sorry, here this minus and this minus simplifies, so I have a plus here also. So I just recovered the usual formula. Okay, the entropy is the internal energy, or usually you write it in the other way around. It's log z, which is the free energy. Okay, or minus log z is the free energy, is the entropy minus the inverse temperature times the internal energy. Okay, this is what you usually call F, the free energy. Okay. Now, all these things are functions of this temperature, of this inverse temperature beta. Okay, because this was the parameter that enters the Boltzmann distribution. Okay. Okay. But you see that you can equivalently see these functions. So if you fix epsilon of beta if you say that it's equal to some value E, then there exists a beta of E such that indeed this relation is true. This beta of E is given by the inverse of this function. And just what I did is nothing. I just said this number, the internal energy, which is a function of beta, is equal to some value E. Okay. So now if instead I want to think of this, of all these objects as functions of this number E instead, I can, because there exists a beta such that this relation is true by definition. And this beta is given by this relation. That may be impossible to compute practically, but there you can inverse this function, and this tells you, if you fix an E instead of a beta, which beta corresponds. Okay, just switching the variable from beta to the internal energy. So now this relation expressed instead as a function of the internal energy, not anymore as a function of the inverse temperature, reads S of E now is equal to beta of E, which is given by this relation here, times E, this is this term, plus log of Z that depends on beta, which is a function of E. Okay. Where this beta of E again is given by this relation. Let me write it again. We have S of E. So the initial relation we had was S of beta, which was the Shannon entropy of the Boltzmann distribution at inverse temperature. Beta was equal to beta, the internal energy when inverse temperature is beta, plus log Z of beta. And by just renaming this thing E, I just re-express this equation as a function instead of E. Okay. Okay. It is equivalent, it's just that I change in my mind which parameter is fixed or not. In the first interpretation, it is the inverse temperature which is fixed, and the internal energy is a consequence, is fixed by the inverse temperature. My control parameter here is the inverse temperature, and the internal energy is fixed, while here, it's the other interpretation. My control parameter is the internal energy, and there is an associated inverse temperature. We already discussed this kind of duality when we did the Lagrange function. And now, if I compute the derivative with respect to this constant E, which represents the internal energy, I obtain beta. This beta is a function of E, by the way. I obtain beta of E plus E d beta of E over dE plus d log z beta over beta d beta e over dE. I just use the chain rule here to compute the derivative of this term. The chain rule of derivatives. I have a function of a function. I have a function which is this log z, which depends on this function of e. So if I want to take the derivative with respect to e, I first derive with respect to the function beta of e, which is this term, and then I derive the beta of e with respect to e. Okay? All right, and this is beta of e plus e d beta of e dE minus this thing is actually the internal energy. We will show it times d beta of e, and this internal energy is fixed to be E because we have fixed the value beta to the proper function so that this object is equal to E. So these two things cancel. I obtain beta of E. So I have shown that indeed dSE over dE is indeed inverse temperature. So to see the remaining thing that we didn't show is d log z over d beta is what is the derivative with respect to beta of the log of sum of x of exponential minus hx times beta. And this is what? The derivative of the log is the derivative divided the log of f of x is f prime of x over f. So this is sum of x exponential. I derive an exponential. What I get here, if I derive the numerator with respect to beta, is minus hx divided by z, which was this thing. And this is exactly minus internal energy. Do you see it? This is the average of the Hamiltonian with a minus. So it's minus the internal energy. You see it? So we've just proved that starting from the Shannon entropy of the Boltzmann distribution, and by not anymore thinking as beta being the fixed parameter and the internal energy, not thinking anymore as beta as the control parameter, which means the one you can change, and the internal energy being fixed by this beta, we just switched their role. We interpreted the internal energy as the control parameter, the thing you can change, and therefore the temperature is fixed. And if we take the derivative of this entropy with respect to E, we indeed recover this beta. So we recover the thermodynamic definition. Okay, so this computation is in my notes. If it was not as clear as the rest, try to do it again. And just the thing here is to understand that you can switch this role of what is your control parameter and therefore what is fixed. Okay, I can change this from internal energy to inverse temperature or vice versa. Okay. And I'm sorry I'm late, but we started late. Okay, but, it's done. All right, so I hope you understood things. Do you have questions or the others? Okay. So we'll close this.